All right, good evening, everybody. Hope everybody's doing well. So, tonight we begin our discussions of really the different types of organic compounds that you come across. Remember, organic compounds essentially have to have carbon as part of their structure. If you don't have a carbon in your compound, then the compound can't be organic. You have to have carbon as part of your structure in order for that carbon to be, or in order for that compound to be organic. Now, in chapter 11, we take a look at a bunch of different types of organic compounds that are classified as hydrocarbons. What does it mean for an organic compound to be a hydrocarbon? Well, these are organic compounds that contain only carbon and hydrogen. So the only two elements that you have present in a hydrocarbon would be carbon and hydrogen. The difference between hydrocarbons is the type of bonding that you have between carbons. And specifically tonight, in this office hour, we're going to focus on what are known as alkanes. So, in terms of a definition, what do we talk about when we talk about alkanes? Well, they are hydrocarbons that contain only carbon to carbon single bonds. Now, as we are about to discuss, and as you saw in the first part of the lecture notes for chapter 11, there are different types of alkanes depending on how the carbon atoms are connected. But what really defines an organic compound as an alkane is that it's a hydrocarbon. So the only two elements that are present are carbon and hydrogen. And the only type of bonding that you have between the carbons are single bonds. Okay? So the first type of alkene that we come across are what are known as your continuous alkanes. What defines an alkane as a continuous alkane? Well, here, all the carbon atoms are connected in a row. And one of the reasons why I like to put the term row in quotation marks is because, in essence, it doesn't have to be in a straight line, so to speak. Essentially, the carbons have to be connected one after the other, after the other, after the other, after the other. So, in other words, you start on one end with a carbon that's attached to one other carbon, and then that next carbon is attached to one other carbon, so forth and so on, until you get to a carbon that really is not attached to anything else besides the thing that's attached right before it. One of the practical examples I like to give to sort of maybe something to relate to is if you think about marching in single file. If you're marching in single file, you have one person after the other, after the other, after the other, after the other, after the other. One of the common themes in the realm of organic chemistry is the idea of naming. And as we talked about in the notes, naming is essentially based on what is known as the IUPAC system. IUPAC stands for International Union of Pure and Applied Chemistry, that essentially they're kind enough to abbreviate as IUPAC. One of the common themes in the IUPAC system has to do with having what is known as a parent or main chain. Now, as you will see in chapter 11 itself, the parent or main chain will mean different things for different types of organic compounds. But essentially, each type of organic compound that we come across in terms of naming, one of the things we're going to do very, very frequently, not always, but very, very frequently, is we're going to look for and find this main or parent chain. And the additional commonality is that throughout the IUPAC system, there are prefixes for essentially 1 to 10 carbons. And in fact, there's even larger, which we don't discuss in this course. But the prefixes for 1 to 10 carbons in this course, it's one of the things that I expect you to know. Okay, so just to mention that there are carbon parent or main chains that can have more than 10 carbons, and there are prefixes for that as well. But for our purposes and for this course, the prefixes I expect you to know, when we went over meth, eth, pro, but, and then Greek takes over from there, pent, hex, hept, oct, non, and dec. Those prefixes are really going to be a common theme throughout our naming as we go through the different functional groups in chapters 11, 12, and 14. So those are prefixes that you have to memorize and you have to know. Right? And again, if you're joining us, you can jump in, use the chat, or you can just unmute and ask questions, of course, as we go along. The other thing to mention, well, in general, and then we'll go back to continuous alkanes in a second. Sorry. I don't know why it went blank. Let me just see what happened. Oh, that's because I had this all the way at the end. So let me just move that back up. So let's just do this. Let's just cut. And paste. Put that there. All right, now we can. So one of the other things to mention in general, and then we'll go back to continuous alkanes in a moment, is that alkenes, sort of independent of what type of alkane it is, alkanes have names that end in ANE. So if you take a look at the name of an organic compound, and you see it ending ANE, you'll be able to recognize it as an alkane. And tonight we'll talk about continuous alkanes, we'll talk about branched alkanes, we'll even talk about cycloalkanes, we'll probably also talk a little bit about haloalkanes, time permitting. Essentially, all these types of compounds, at the end of their name, they end in ANE. That's how you're able to recognize it as an alkane. Now, for continuous alkenes, the main chain is essentially the compound itself. So basically, the entire compound is basically the main or the parent chain. There's nothing else additional. Because as you saw in the notes, and as we'll talk about, there are types of alkanes, and there's plenty of types of organic compounds where you have a parent or main chain, but then you also have what are known as branches attached to it. We'll get to that in a little bit. But for your continuous alkenes, the main or parent chain is the compound itself. So basically, with those prefixes, and with the ending ANE, essentially you have all that you need for continuous alkanes that have 1 to 10 carbons associated with them. So let's look at an example. And what I want to do with this example also is to talk a little bit about the different ways that organic compounds can be drawn. First off, let's focus just on drawing a structure for hexane. And let's do it in the most, to me, the most simplistic way. And that most simplistic way would be to draw the expanded structure for hexane. So what do we talk about when we talk about an expanded structure? An expanded structure shows all of the bonds between all of the atoms. Everything is shown. Nothing essentially is left to the imagination. Everything is shown. So let's decipher the name hexane. The hex would tell us how many carbons in a row, 6. And what type of bonding would you have between the carbons? The ANE tells us that we're dealing with an alkane. So that tells us that the type of bonding that we're going to have between the carbons is single bonds. So basically, I would put my 6 carbons in a row. 1, 2, 3, 4, 5, and 6. Again, in a row means one after the other, after the other, after the other, after the other. Single file. First carbon bonded to the second carbon bonded to the third carbon bonded, so forth and so on. Now, because it's an alkane, the rest has to be filled in with what? The rest has to be filled in with hydrogens so that every single carbon has how many bonds total? Remember, the magic number for carbon is 4 bonds. It could never, ever have more. There are some facets of organic chemistry that we won't discuss where there are carbons in certain instances that have less. We're not going to get into that. So basically, for our course, for all intents and purposes, every single carbon atom that you come across should have 4 bonds total. So let's fill in the hydrogens, going from left to right. 3 here, because this carbon only has 1 bond coming off of it before. This carbon has 1, 2 bonds coming off of it. So that would lead us to 2 hydrogens. Then I would have 2 hydrogens here, another 2 hydrogens here, another 2 hydrogens here, and then 3 hydrogens here. And what I would have when I put that all together is my expanded structure for hexane. Now, another type of structure that we come across are your condensed structures. So condensed structures are similar to expanded in the sense that essentially the only, let me put it this way, the only real difference between condensed and expanded structures is that in condensed structures, carbon to hydrogen bonds are not shown. Each carbon and its attached hydrogens are written as a group, where the number of hydrogens that you have is sort of written as a subscript. So for example, if we talked about in the notes, you know, if a carbon has 3 hydrogens attached to it, that would be written as CH3. If a carbon has 2 hydrogens attached to it, that would be written as CH2. And if a carbon has 1 hydrogen attached to it, that it would be written as CH. And the reason why I'm drawing the other lines in is, of course, because at the end of the day, carbon should have how many bonds total? Carbon should have 4 bonds total. So if we were going to take this expanded structure and make it into a condensed structure for hexane, how would we do it? Well, the first carbon we come across on the left has 3 hydrogens attached to it. So we would write that as CH3. That's connected to the next carbon over here, which has 2 hydrogens attached to it. So that would be written as CH2. And then continuing on, I'd have another CH2, another CH2, 1 more CH2, and then CH3. And what you would have on the bottom here is a condensed structure for hexane. The key thing to understand about in the condensed structures is that the bonds that are shown here are bonds between the carbon atoms. Those are the bonds that are shown here. They are the bonds between the carbon atoms. So this would be the condensed structure for hexane. One other type of structure that's discussed and that we want to talk a little bit about are your skeletal structures. Now, from my perspective, these are probably going to be the most difficult for you to learn. The nice part about them, in a sense, and I don't know if I'd even call it nice, because I don't know if skeletal structures are. They have a very good purpose, and sometimes it's actually easier to look at a skeletal structure, and we'll see that tonight as part of our discussions. But they are the most difficult to sort of learn about, and the reason for that is that carbons are not shown and hydrogens are not shown. In a skeletal structure, where do we find carbons? We find carbons in two places: where a line comes to an end, or at points where lines touch each other. Either two lines touching at a point, three lines touching at a point, or even four lines touching at a point. That's where we would find carbon atoms. Now, the points are not shown. It's just where the lines touch. Now, what about hydrogens? Well, basically, the number of hydrogens is quote unquote implied, because we look at the skeletal structure, and when you look at a carbon, you say to yourself, okay, how many bonds are being shown coming off of that carbon in the skeletal structure? And whatever that number is, it's then going to need X number of hydrogens to get up to 4 bonds total. Let's sort of discuss it this way. If I was going to draw a skeletal structure for hexane, one way to draw it would be as follows. And what I'm going to do is I'm just going to put arrows where the carbons are. So we'd have 1, 2, 3, 4, 5, 6. So our first carbon would be here, where the line comes to an end. It's bonded to the next carbon, which would be here, because it's where this line and this line touch. And then this carbon here would be bonded to this carbon here, because it's where this line and this line touch. And then this carbon would be bonded to this carbon here, because it's where this line and this line touch. And then this carbon would be bonded to this carbon here, because it's where this line and this line touch. And then this carbon would be bonded to this carbon here, and because that's where a line comes to an end. So these lines are essentially bonds. And where a line comes to an end, or the point where two lines meet, intersect, that's where you find the carbons. Now, how would you know how many hydrogens each of these carbons have? Okay, so if I look at this carbon here, in the skeletal structure, this carbon has 1 bond coming off of it. It's got 1 line coming off of it, which means that there has to be 3 hydrogens. Why? Because 1 plus 3 would give you 4. If I take a look at this carbon here at the top, this carbon here at the top has 1, 2 bonds coming off of it, which means how many hydrogens are there? It means there are 2 hydrogens that are there. Let me just see if I can write that a little bit better. There would be 2 hydrogens that are at this carbon right here. Here, 2 bonds, 2 hydrogens. Here, 2 bonds, 2 hydrogens. Here, 2 bonds, 2 hydrogens. And then finally, this carbon only has 1 bond coming off of it, and therefore there would be 3 hydrogens. So if you think about it, you have CH3 connected to CH2, connected to CH2, connected to CH2, connected to CH2, connected to CH3, which would be the structure for hexane. Now, I'll be honest. When I draw continuous alkanes or the next type of alkane that we talk about, branched alkanes, when I give them to you, ask you about them, I tend to shy away from skeletal. So if skeletal's a little bit tricky right now, it's not going to be the end of the world. But when we get to, and if we saw in the notes, when we get to this, what are known as cycloalkanes, those ring structures, I do like to draw those in skeletal form. So we have to sort of come to an understanding of skeletal structures. We might not have to master them so much yet, but we have to come to an understanding of them. The other thing I'll mention is that in terms of drawing structures, whether you want to draw it expanded, whether you want to draw it condensed, whether you want to draw it skeletal, that's all up to you. The only requirement that I basically have is that you draw it correctly. As we go through, and even in the notes, I give you some tips about what I think will help you draw structures correctly. But the bottom line is you could sort of draw it however you want. The only requirement is that you draw it correctly. All right. So your continuous alkanes are the first type of alkane that we come across. All right.
Can we do another skeletal structure? Sorry.
No, that's okay. Of course. Yeah, no, feel free to jump right in. Sure. Yeah, we could do another skeletal structure. Sure.
Thank you.
Let's say I wanted to do, you want to do one of another continuous, or do you want to go forward a little bit and then do one when we talk about the branched?
Either one's okay. I'm just not sure how to count the hydrogens inside the skeletal structure.
All right, so let's do another one right now. So let's do octane.
Thank you.
Of course. All right. So for octane, you would have 8 carbons in a row. So one way to draw it would be like this: 1, 2, 3, 4, 5, 6, 7, 8. So essentially, where would our carbons be? Our carbons would be here, 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 and here. Okay, so this carbon here in the skeletal structure is showing how many bonds coming off of it. 1, which means how many hydrogens would there be? Because again, the goal is to get up to 4 bonds total. So that would mean that this carbon over here has to have 3 hydrogens. So essentially, what would that look like? That would look like a CH3. Now, this one over here at the top, this carbon is showing how many bonds coming off of it. 1, 2. So how many hydrogens would there be off of that carbon? There would be 2 hydrogens. So essentially that CH3 would be connected to a CH2. Okay, let's go to the next one. So this carbon here has 1, 2 bonds coming off of it, which means how many hydrogens are there? There would have to be 2 hydrogens. So this CH2 here would be connected to another CH2. So for this example, you'd have CH2, CH2 would be again next, connected to another CH2, connected to another CH2, connected to one more CH2, and then on the end, this carbon here would only have 1 bond coming off of it, so it would be a CH3. So you'd have 1, 2, 3, 4, 5, 6, 7, 8. Let me actually do one more example, and for this next example, we'll just talk about finding the number. We're not going to worry about names so much, but I want to do something a little bit different to make sure that we understand skeletal structures. All right, so let's take a look at the following compound here. Let me just draw it again one more time. So we got 1, 2, put a line going down here, line up here, line going down, line going down, line going down. All right. So for this example here, all we want to do is we want to figure out how many hydrogens would there be on each carbon. All right. So let's start with this carbon here on the end. So if I look at this carbon here, how many bonds are shown coming off of this carbon? Only one bond right here. So because the next carbon is right there. So because this carbon has one bond attached to it, how many hydrogens would be on that carbon there? There would be 3 hydrogens that are present. All right. So then this carbon is connected to this one up here. This carbon is showing 1, 2 bonds coming off of it. So how many hydrogens would be attached to that carbon? There would be 2 hydrogens attached to that carbon. Now, this carbon is actually connected to a carbon that's right here. And I know there's a carbon there because 1, 2, 3 lines touch right here. That's the point where the 3 lines intersect. So in fact, there would be a carbon right there. Now, as I sort of hinted, how many bonds are coming off of this carbon right here? There's 1, 2, 3. So how many hydrogens would be on this carbon right here? There would only be 1 hydrogen attached to it. Okay? There would only be 1 hydrogen attached to it. Now this carbon here is attached to a carbon down here because this is where a line comes to an end. So there's another carbon right here. How many hydrogens are attached to this carbon? Well, this carbon has 1 bond, 1 line coming off of it. And therefore that carbon would have 3 hydrogens attached to it. Now this carbon, going back to this carbon right here, it's also attached to this carbon right here. And I know there's a carbon there because I actually have 1, 2, 3, 4 lines that touch right at this point here. Now, how many hydrogens would that carbon have? Well, this carbon is showing 1, 2, 3, 4 bonds, which means that this carbon actually has no hydrogens. And is it possible for a carbon to have no hydrogens? Absolutely. If that carbon is attached to 4 other carbons, then it's absolutely possible that you might not have any hydrogens attached to it. And then,
Thank you. That helped a lot, that one.
yeah, and that's why I wanted to do this one. And just to also finish it up, you have a carbon up here, a carbon right here, and a carbon there. And each one of those has 3 hydrogens. So in fact, if I were to make this into a condensed structure, it would actually look like the following. CH3 connected to CH2, connected to CH, with a CH3 going down, then continuing to the right, a C, no hydrogens, with a CH3 going up, CH3 to the right, CH3 going down. This would be your corresponding condensed structure of that compound. All right, good. Absolutely, fire away with questions. This is sort of your time to ask. So before I talk about branched alkanes, are there other questions that you want to go over from what we've done? So or what you looked at in chapter 11 so far?
No, thank you. Not yet.
Okay, sounds good. Okay, all right. So I'll continue then. All right. So the next type of alkane that we talk about are your branched alkanes. Now here, these are alkanes in which all of the carbons are not connected in a row. Okay, so for your continuous alkanes, all the carbons are connected in a row. In your branched alkanes, all of the carbons are not connected in a row. Now, essentially, your branched alkanes have two parts. First off, you have the parent or main chain, which is the longest continuous carbon chain that is present. So essentially, we're sort of looking for the longest continuous alkane that's part of the compound. But the difference here is that there's something else, there's other things that are present besides the parent or the main chain. So for branched alkane, the parent or main chain is the longest continuous carbon chain that's present, the largest number of carbon atoms connected in a row. And then your second part are what are known as branches. Branches are carbon groups attached to the main or parent chain. So they're not a part of it, but they are attached to it. Now, in this course, there are 4 branches of what are known as alkyl groups that we need to know. The first one has only 1 carbon. Now, as you saw in the notes, when we went over these, and we're going to do this again now, the bond that sort of looks like it's not connected to anything is essentially your point of attachment to the main or parent chain. So, coming off the main or parent chain, you have a CH3 group. This branch is what is known as methyl. Now, just to show you, if you go back to this example here, okay, the longest continuous carbon chain is 1, 2, 3, 4, 5. Now, notice there's actually a bunch of ways of getting 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. In this course, if that's the case, they should all lead to the same answer. That's not always the case, but for our purposes and for this course, they will always lead to the same answer. One of the things that I talked about in the notes, and I would recommend, is that once you find the parent or main chain, circle it. Because the way that I use this to my advantage is that I know whatever I don't circle has to be a branch. So this particular compound has 1, 2, 3 branches. And each one of them are examples of what? Each one of them are examples of methyl groups. Point of attachment, CH3. Point of attachment, CH3. Point of attachment, CH3. They're all methyl groups. Okay? So that's the first branch. The second branch has your point of attachment to the main chain connected to a CH2, and the CH2 then connected to a CH3. And in reality, it has to be in that order. This branch is what is known as ethyl. Let me show you what that might look like. Okay. So if you take a look at this example here, the longest continuous carbon chain that's present is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. They would both lead to the same name, which would absolutely be the case. So if we can go straight across to designate the parent or the main chain, let's go straight across. So now, if I ask you, how many branches does this compound have? This compound has one branch. How do I know that? The way I know that is that there's one bond coming off the main or parent chain. This bond right here is coming off the main or parent chain. So, point of attachment, CH2, CH3, what branch is that? That's the ethyl group. This is a singular branch. Point of attachment, CH2, CH3, that is what is known as the ethyl group. The last two actually have 3 carbons associated with them. But in reality, that's where their similarity ends. The first 3 carbon branch is what is known as propyl. So for propyl, you have your point of attachment to the main or parent chain connected to CH2, connected to CH2, connected to CH3 in that order. Okay. CH2, CH2, CH3 in that order. As compared to what is known as isopropyl, which also has 3 carbons total, but here your point of attachment is connected to a CH. And then coming off of that CH in 2 different directions are CH3s. That's the isopropyl group. Now I know isopropyl usually gives every students some difficulty. So let me just show you in an example what an isopropyl group would look like. Okay, let me just double check. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. And what I'm doing here, which I call my diligence, my due diligence, is something you really want to do, especially when it comes to naming, which we'll get to some examples of naming in a few minutes. You want to make sure that you correctly find the main or parent chain. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. The bottom line is the only way to get the longest continuous carbon chain is to go straight across. Now, here's the point of this question. How many branches does this compound have? This compound only has 1 branch. How do I know that? I know that because there's 1 bond coming off the main or parent chain. So there's only 1 branch here. What is this branch? Well, look what you have. You have your point of attachment connected to CH, and then coming off the CH in 2 different directions are going to be CH3s. Notice, point of attachment, CH, and then 2 different directions are your CH3s. What branch is this? This is the isopropyl group. So that's essentially what the isopropyl group would look like as a branch. If you had propyl here, which you could actually have, The difference would be is that you'd have your point of attachment connected to CH2. That CH2 would be connected to another CH2, and then that CH2 would be connected to a CH3. That's if you had propyl, which you don't have here. You have isopropyl. Okay. You have to commit those branches to memory. Those are the 4 alkyl groups that I need you to know for the course. There are larger ones. We won't talk about those. These are the 4 that I need you to know for the course. Okay. So one of the big aspects is naming branched alkanes. Okay. So what do? Number 1, find the main chain and name it based on the continuous alkane name. And what that does is that it gives what is known as the parent name for the compound. Second, number the carbons in the main chain starting from the end closest to a branch. The goal for branches in branched alkanes, the goal for branches is to have the lowest numbers possible. Whether there's 1 branch, whether there's 2 branches, whether there's 3 branches, the goal for branches is to have the lowest numbers possible. Lowest numbers possible. The main way to ensure that, which usually solves most of the examples in a sense, is to start at the end closest to a branch. Now, there are some instances that when you go from, and when you number the carbons in the main chain, you have to number starting from an end. So in a branched alkane, there's only 2 ends. So you have to either start from one end or start from the other end. There's no other places to start. In a branched alkane in the parent or main chain, there's only 2 ends. You have to start from an end. You basically want to start from the end closest to a branch. Now, there's some instances that when you go from one direction or the other direction, one end or the other end, the first branch would be at the same carbon. Then what it really comes down to is lowest set of numbers. Lowest set of numbers. And in this course, we won't give you any examples where you'd have to like really apply other sort of quote unquote tie-breaking methods. You know, if you go from both ends in the first branch, it would be at the same number. There's going to be a direction that gives the lowest set of numbers. Now, here's one important point. Every branch has to have a location in the name, even if it is the same branch on the same carbon. Okay, so in your branched alkanes, and this is often true in most naming instances. There's some exceptions to this that we'll see, but in reality, the way I approach it is that every single branch, somewhere in the name, there has to be a number giving its location, even if it's the same branch on the same carbon. If you got 2 methyl groups on the same carbon, it's possible, but you better give their location, both of them, by giving that number twice. And you saw that in the notes, and I'm sure we'll come across an example of that as we work through some problems. Every branch has to have a number giving its location. All right. And then finally, third, give the names and locations of branches in alphabetical order in front of the parent name. One technical issue, as you saw in the notes, in a name, dashes separate numbers from words, commas separate numbers. The commas to me are more important than the dashes. Because if you have two carbons at carbon two methyl groups at carbon two, you want to write 2,2, you don't want to write 22. So the commas to me are a little bit more important. You leave out a dash, it's not the end of the world. Comma is more important to me than a dash. The other thing is that if you have more than one, in other words, if you have a branch that's there more than one time, you don't write the branch name over and over and over again. We talked about prefixes. Di, tri, and tetra, which would be used to name branches that appear more than once. If a branch appears more than once. So if you have two methyl groups total in the compound, you don't write methyl-methyl, you write dimethyl. For some reason, if you have three ethyl groups in the compound, you don't write ethyl-ethyl-ethyl, you write triethyl. All right? All right, so let's do some examples. And I'm going to pull these from the back of the chapter. Right now, I'm looking at page 393, just to give you sort of a reference of this. So let's do a couple one. Let's start with letter A. Sorry, I won't even, you just find them on the page. Here's the first one. So how would we name this compound here? Longest carbon chain that's present is how many carbons long? 4. Bunch of ways of getting it. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. They should all lead you to the same name. They absolutely do. So let me circle one of those ways. Again, if you can go straight across, I would recommend going straight across. 4 carbons, all single bonds, would give us a parent name of what? Would give us a parent name of butane. Okay, so that's our parent name. 4 carbons, all single bonds, would give us a parent name of butane. How would we number the carbons in that chain? There's 2 ways of numbering it. I can start from the left end and go to the right. I can start from the right end and go to the left. We want to start at the end closest to the first branch. So there are how many branches here total? 2. They're both on the same carbon. To give them the lowest numbers, the only correct way to number here would be to go from right to left. So that the 2 branches are both attached to carbon number 2. If I went the other way, both branches would be attached to carbon number 3. Both branches rather be attached to carbon number 2. Now, how do I give the names and locations of the branches? Watch. 2, 2. I probably should have gave myself some more space. I apologize. I'm just going to erase that for a minute. So 2, 2 dimethyl butane. There's 2 methyl groups, dimethyl. What carbon numbers are they attached to? They're both attached to carbon number 2. So 2, 2 dimethyl butane would be the answer here for this structure. All right. All right. Let's take a look at this example here. Okay, this is another example from page 393. Okay, so this was our first example. I guess we'll call that A. Let's call this B. All right, so longest continuous carbon chain in this example. 1, 2, 3, 4. No. 1, 2, 3, 4. No. 1, 2, 3, 4, 5, 6. Yes. 1, 2, 3, 4, 5, 6. Yes. It doesn't have to be in a straight line to be in a row. All the carbons have to be are connected to each other. So one way of getting our parent or main chain correctly here would be as follows. Now notice there's still two ends. There's an end here and there's an end here. So 1, 2, 3, 4, 5, 6 carbons in a row, all single bonds, would give us a parent name of what? Would give us a parent name of hexane. All right. In terms of numbering first of all, how many branches do I have? I still have 2 branches, or I have 2 branches. One here, one here. They're both still methyl groups. I have to number the carbons starting from here or from here. I have to put carbon 1 here or carbon 1 here. Which way would give me the lowest, would be the end closest to the first branch? It would be to start over here. That's carbon 1. And then go 2, 3, 4, 5, 6. If I went the other way, my branches wouldn't be until 1, 2, 3, 4, and 5. 2 and 3 is definitely better than 4 and 5. So now how would we write those branches in front of the parent name? 2, 3, again, dimethyl hexane. There's 2 methyl groups. That's where the dimethyl comes from. One of them is at carbon number 2. The other one is at carbon number 3. 2, 3 dimethyl hexane.
Can you repeat how you get the 2 and the 3?
Sure. So if you look at so you understand how I came up with this as my parent chain? How this is 6 carbons? Is that part okay?
Yes.
Okay. So there's 2 ways of numbering the carbons in the chain here. And you have to start from an end of the parent or main chain. So you have to start here or you have to start here. If I start here, the carbon numbers are 1, connected to 2, connected to 3, connected to 4, connected to 5, connected to 6. So this methyl group is attached to carbon number 2. This methyl group is attached to carbon number 3. Now, the reason why I don't use the other end is because if I did, this carbon would be attached to carbon number 4. This methyl group would be attached to carbon 4. This methyl group would be attached to carbon 5. You want, the branches want the lowest numbers possible. So this branch is attached to carbon 2, 1 connected to 2, connected to 3, connected to 4, 5, 6. This methyl group is attached to carbon 3. Make sense?
Yes, thank you.
Okay, of course. Absolutely. All right. All right, let's do do one that has some different branches. We haven't come across that just yet, so I think I'll have to sort of make this one up myself, which is fine. Let's do this. All right. Just make sure I got what I want. Okay, we're good with this one. Okay, longest carbon chain in this example here would be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Let me see anything else. 1, 2, 3, 4, 5, 6. No. 1, 2, 3, 4, 5, 6, 7. No. So 8. So 2 ways of getting it. Pick either one. If we can go straight across, let's go straight across. So 8 carbons, all single bonds, would give us a parent name of what? Would give us a parent name of octane. The reason why I put this example up is because if I number the carbons from left to right, here's the number: 1, 2, 3, 4, 5, 6, 7, 8. Let's compare that to what the numbering would look like if I go from right to left, and I'll put that in blue. 1, 2, 3, 4, 5, 6. That should come out as a 6, 6, 7, 8. Okay. So here's a little bit of the conundrum. If I go from left to right in red, first off, how many branches do I have total here? I have 1. This is 1 branch. 2, 3. So I got 3 branches total. If I go from left to right, which is in red, my first branch is attached to carbon 3. If I go from right to left, which is in blue, my first branch is also attached to carbon 3. So now, how do I know which way is correct? Now it's going to come down to lowest set of numbers. If I go from left to right, which would be, and actually, you know what, just to keep it nice and clear, I was going to draw it in red just to be consistent. If I go from left to right, there are 3 branches. So when I give the name, how many numbers must there be in the name for the branches? There's got to be 3 numbers. If I go from left to right in red, the 3 numbers I would have are 3, 5, and 6. 3, this branch is attached to 3. This branch is attached to 5. This branch is attached to 6. But on the other hand, if I go from right to left, what 3 numbers would I give? Well, 1 branch is attached to 3. Another branch is attached to 4. The third branch is attached to 6. So, which is correct? Is there a difference? And the answer is yes. The lowest set of numbers is actually right to left. 3, 4, and 6 is better than 3, 5, and 6. So in fact, the correct way to number the carbons here in this compound would be from right to left. Now, at carbons 3 and 4, I've got methyl groups. So we're going to write the name dimethyl. What branch do I have attached to carbon 6? At carbon 6, I have ethyl. When you go to write the name, and this is not the biggest deal in the world, but when you go to write the name, di, tri, and tetra are not used for alphabetizing. So in fact, I would put the ethyl portion first. 6-ethyl dash 3, 4 dimethyl octane. 6-ethyl 3,4 dimethyl octane. If you wrote 3,4 dimethyl first and the 6-ethyl after that, would I be okay? Yeah, I'd probably be okay with that. But if you didn't put in one of those numbers, that's going to cause a little bit of an issue. All right. So I think if you understood this one, and you understand about making sure you find the right parent or main chain by not always assuming it goes straight across, you've got a pretty good idea of how to name branched alkanes. All right. And I think we're just about out of time for this evening. Okay. Any questions in general before we say goodbye for tonight?
No, I'm good.
Okay. So as far as chapter 10 homeworks go, I'm going to start grading them tomorrow. So hopefully you'll have that back by the end of the weekend. If not, Monday or Tuesday, the latest. I'm going to scan them and upload them to Canvas where you submitted them. So you'll have them back. Keep working on chapter 11. Next week's Zoom office hour, we'll do cycloalkanes. We'll probably get into alkenes and alkynes, and we'll talk about isomerism as well as part of that. So keep working a little bit through it. Hopefully by the end of this week, you've gotten through much of alkanes. Next week, you want to start to focus on alkenes and alkynes, and then maybe the week after that, the last part of the chapter, and starting to get ready for the first exam as well. All right. All right. Thanks for joining. Stay well. I'm going to post the recording to Canvas sometime later tonight or tomorrow. And again, if you need anything in the meantime, feel free to email me and I'll get back to you as soon as possible. All right.
Great. Thank you so much.
You're welcome. Stay well.
You too.